Welcome to the Deep Dive. Today we're jumping into something really central to modern AI, generative models.
That's right. We're looking at diffusion models and this related idea of flow matching, basically how AI learns to create new stuff.
And our guide is a great tutorial paper, Step-by-Step Diffusion, by Preetam Nakaran and others. The goal is to really demystify how these things work.
Exactly. We want to give you a clear picture of how you go from, well, basically noise to generating something complex and structured, like an image.
So the core problem in generative modeling is learning to sample from some distribution you want, like images of dogs.
Right. You have examples, maybe lots of dog pictures, and you want a machine that can dream up new dog pictures that look just as real.
But that seems like a huge leap. You know, going from random noise to a perfect dog photo in one step feels hard.
It is incredibly hard, and that's the genius of diffusion. Instead of one giant leap, it breaks it down.
And to smaller steps.
Yeah, lots of tiny, much more manageable steps. It turns one impossible sampling problem into many, many easy ones.
Okay, so walk us through that. How does it start? I gather there's a forward process first.
That's right. It's often called Gaussian diffusion. You take your clean data, let's say that perfect dog image, XU,
Okay.
and you gradually add a little bit of noise, then a little more, and more. You get a sequence by 1, by 2, and so on.
So each step makes the image slightly fuzzier, slightly more random.
Exactly. You keep adding small amounts of Gaussian noise independently at each step. If you go far enough, say to step T,
T being a large number.
right, a large number of steps, by the time you get to XT, your original image is basically just random Gaussian noise. It's lost all its structure.
Okay. And is there an advantage to doing it this way?
Well, the neat part is that this forward process is mathematically quite tractable. You can actually calculate the distribution of any noisy version directly from the original X0 without going through all the intermediate steps.
I see. So you can jump straight to a specific level of noisiness.
Precisely. But okay, that's how you destroy the data. The real magic, the generation part, is running this whole thing in reverse.
Right. Starting from pure noise, that XT state, and somehow getting back to a clean image, X0. How on earth do you do that?
Well, you don't do it in one jump. You learn to reverse each small step. So you learn how to go from the distribution at time t, pt, back to the slightly less noisy distribution at time t1, pt1.
Is that easier than the big jump?
Much easier, because pt and pt1 are very similar. They're close. The distributions haven't changed much in one tiny step. So learning the reverse of that step is a more focused, simpler problem.
Okay, that makes intuitive sense.
Uh,
How do models actually learn that reverse step? This brings us to things like DDPM, right?
Exactly. DDPM stands for Denoising Diffusion Probabilistic Models. This was really popularized by Ho and colleagues in 2020, building on earlier work.
And the core idea.
The core idea is to learn the conditional distribution. What's the probability of the previous state, xt1, given the current state, next? And here's a key insight. When the noise steps are small, this reverse conditional distribution, pxt1xt, is also approximately Gaussian.
Oh, so you don't need to learn some weird complex distribution.
Nope. It boils down to learning the mean of that Gaussian. And learning a mean is basically a regression problem. The network learns to predict, essentially, the noise that was added, so it can subtract it out.
So DDPM involves sampling at each step. There's still some randomness as it moves backward.
Yes, it's inherently stochastic. But then came D, Denoising Diffusion Implicit Models from Song and colleagues in 2021.
And what's the difference there? Implicit sounds less random.
Exactly. DDIM is deterministic. Instead of sampling from a conditional distribution, it learns a direct mapping, like a function ft that takes a point from posts and deterministically moves it to a point in pt1.
Like following a specific path instead of randomly stepping nearby?
You can think of it like that, yeah. Like following a velocity field that guides the noisy sample smoothly back towards the original data. This often means you can use fewer steps to get a good result, which is much faster.
Faster generation is always good. But the evolution didn't stop there, did it? What about flow matching?
Right. Flow matching is a more recent and actually more general framework. In fact, DDIM turns out to be a special case of flow matching.
Interesting. So what's the core idea behind flow matching?
It thinks about the process as learning an overall flow. Imagine you have points starting in the noise distribution and ending in the data distribution. Flow matching tries to learn the average velocity, the marginal flow, that describes how the entire distribution moves from noise to data over time.
An average of many individual paths.
Kind of. It looks at these pointwise flows from single noise points to single data points and learns a vector field from that. Like DDPM, it ends up being solvable with regression, predicting these velocity vectors.
And this gives more flexibility.
Yes, much more. It allows for different kinds of paths, like the rectified flows used in models like Stable Diffusion 3, which can be even more efficient and direct, potentially leading to higher quality generation in fewer steps.
So beyond these different theoretical approaches, DDPM, DDIM, flow matching, what are the practical things people are working on?
A huge focus is on samplers.
Mm.
How do you actually implement these reverse steps efficiently? Can we get great images in, say, 10 steps instead of 1,000? That's a major research area.
And how the network itself is set up.
Yeah, parameterization. Does the network predict the noise? Or does it try to predict the original clean image big zero directly? Different choices have different trade-offs.
And there are still open questions, right? Like generalization.
Absolutely. A big one is understanding how these models generalize from the training data. You want them to create novel images, not just slightly modified copies of what they've seen. Avoiding data replication is crucial.
So wrapping this up, we've gone from this huge challenge of generating data from noise,
To breaking it down into manageable steps. First, probabilistically with DDPM,
then deterministically with DDIM,
and now with the more general framework of flow matching, which offers even more design freedom.
it really shows the power of breaking down complexity, taking one big, hard problem and turning it into a sequence of smaller, solvable ones.
It's a powerful concept, and as you think about this, maybe consider where else that principle applies. Taking something that seems overwhelming, intractable, and finding a way to approach it step by step, that's not just for AI, is it? It's a pretty fundamental strategy for tackling almost any complex challenge.